The next objective will be to write the equation of a tangent line and a normal line. The most important part of this objective is writing the equation of a tangent line. You're going to be asked to write the equation of tangent lines very frequently throughout the year. It shows up a lot on the AP test, so that's really important. A normal line is less common. It's important to know what it is, but you won't see it quite as much. A tangent line is a straight line that touches a function at exactly one point. So if this blue line is our function, the tangent line hits at a point and skims along the graph and just touches it exactly once. And then a normal line is a line that is perpendicular to the tangent line. So this line, which I'm making green, is perpendicular to that red tangent line. So that's what a normal line is. So a normal line also touches a curve at exactly one point, but it's, again, perpendicular to that tangent line. Now, since it's perpendicular to the tangent line, its slope is the opposite reciprocal of the tangent line's slope. So let's say our tangent line has a slope equal to, I don't know, 4/5. Then the slope of the normal line would be perpendicular to that. So it would be the opposite reciprocal. Now remember, opposite means you change the sign. So if the first slope was positive, the next one's going to be negative, or negative to positive. And then reciprocal means you flip the fraction. So the slope of the normal line would be -5/4. So I made it positive to negative and I flipped the fraction. That's the reciprocal part. And one thing to keep in mind, the most important thing to keep in mind, is that the slope of the tangent line is the derivative. So always remember that the point of finding the slope of the tangent line is because it represents the derivative of the function at that point. We also see the verbiage instantaneous rate of change, which is the same as the slope of the tangent line and the derivative. Those three things are synonymous. Here's another example of what a tangent line looks like on a graph. If you pick any point on a function and draw a tangent line, depending where you draw that point, or which point you choose, the slope of the tangent line might be different. So kind of all along, the slope of the tangent line changes. So if you look at a graph and say the graph happens to be increasing, like right here where I'm highlighting blue, the graph is increasing. The graph is increasing right here. The graph is increasing right here, where from left to right the graph is going up. Think about what type of slope those points or those tangent lines have. What do you guys notice about the slope of the tangent line at all of these points? We should notice that when the graph is increasing, the slope of the tangent line is positive. All of these little lines that I just drew have positive slope. And if we look at places where the tangent, or where the graph is decreasing, which I'm going to highlight in green, the slope of the tangent line is going to be negative. So all these little tangent lines have negative slope. And that slope is changing still depending where we draw it. Some places are steeper than others, but all the places where the graph is decreasing, there is a negative slope to the tangent line. So all these places that I drew in green are decreasing. The slope of the tangent line is negative, and the derivative is negative, less than 0. And the opposite is true for the places where the graph was increasing. So all the places where the graph was increasing, the slope of the tangent line was positive, greater than 0, and that means the derivative is greater than 0 at those places. And then the third case that we should think about is the places where the graph is neither increasing nor decreasing, and that would be the very tops of the mountains and the very bottoms of the valleys, the places where the slope is 0. So anywhere that the slope is, or you have a horizontal tangent line, the slope of the tangent line is equal to 0. And the derivative is equal to 0 at those places. Now we're going to look at an example where we actually find the slope of the tangent line and the equation of the tangent line. To find the slope of the tangent line, we first need to find the derivative. So if we are given a function, we want to find its derivative, f prime of x. So I'm going to use the power rule, and the derivative of this function, I multiply the 2 by the 3 and get 6x to the first power minus the derivative of 2x would be 2, and the derivative of 4 is 0, because the derivative of a constant is always 0. So there's my derivative, and I want to evaluate the derivative at -2. So I find f prime of -2, meaning I plug -2 into the derivative. So 6 times -2 minus 2 gives me -14. And now I want to write the equation of the tangent line to the graph at x equals -2. So this -14 that I found in part A is the slope of the tangent line. And to write the equation of the tangent line, I need a point on the graph, because to write the equation, so imagine you've got some curve and at the tangent line has a slope of -14. I need the coordinates of that actual point, some xy pair, to actually write the equation of the line in point slope form. Remember, point slope is y minus y1 equals m times x minus x1. So I need the coordinates of a point. And the actual point is on the original function. So I want to evaluate the original function at that given x value. So I want to find, for the point, I need f of -2. I'm plugging -2 back into the original function. So that is going to be 3 times -2 squared minus 2 times -2 plus 4. And that gives me 20. So the things that I need, again, are the point, and my point is going to be -2, comma, 20, and the slope of the tangent line, which we found to be -14. So the equation in point slope form for my final answer is y minus the y coordinate of the point, which is 20, equals m, which is the slope, -14, times x minus the x coordinate of the point. Now since it's minus -2, it becomes +2, And that is the equation of the tangent line. And it's okay to leave it in point slope form, as you did in pre-calc pretty often, unless it says to write it in slope intercept form. Now, if you have to find the equation of the normal line, again, this is less common than tangent lines, but a normal line passes through the same point, but it's perpendicular to the tangent line. So since it's passing through the same point, we still need that point on the graph. So we had to find f of -2, which we already found was 20. So our point is -2, 20. And we need the slope of the normal line. Now the slope is going to be the perpendicular slope. So if the slope of my tangent line was -14, this perpendicular slope to that tangent line is the opposite reciprocal. Negative changes to positive, and the reciprocal of 14 over 1 is 1 over 14. So the equation of the normal line in point slope form is y minus the y-coordinate of the point, which is 20, equal to the slope of the normal line, 1 over 14, times x minus the x-coordinate of the point, which is -2, so it becomes +2. And that is the equation of the normal line. Blue was my tangent line. Now this video is getting very long, I realize, so feel free to turn me off and try this on your own. But if you do feel like you need to see me go through another example, I will. Okay, so to write the equation of a tangent line, there are two things you need. You need the coordinates of the point, and you need the slope. So for the point, we are going to find the y-coordinate of the point. We already know the x, so I'm going to plug 1 into the original function. So that's going to be m of 1. And so that will be 1 squared minus 5 times 1 plus 2 over 2 times 1 minus 1, which equals -2. And then I need to find the slope, and for that I need to find m prime of 1, or the derivative evaluated at 1. So first I need to find the derivative, m prime of x. And since we have two expressions being divided, I have to use the quotient rule. So low d high minus high d low over low squared. Low is the bottom. D high, the derivative of the top, 2x minus 5, minus high, x squared minus 5x plus 2. D low, derivative of the bottom is 2, over low squared, 2x minus 1. And I don't need to simplify that, I just need to evaluate that at 1. When I plug 1 into that derivative, I get m prime of 1 is equal to 1. So my point is 1, -2, and the slope, the derivative evaluated at 1 came out to be 1. So now I'm going to use point slope form. Y minus y1 equals m times x minus x1, and that is y minus -2, which becomes +2, equal to 1, that's the slope, times x minus the x-coordinate of the point, x minus 1. And there is the equation of the tangent line. Now, if you were to find the equation of the normal line, remember that the point is the same, so you still find the point by plugging that x-coordinate into the original function. M of 1 came out to be negative 2. And then the slope, the perpendicular slope, is going to be perpendicular to the slope of the tangent line, or the opposite reciprocal. Since the slope of our tangent line was 1, the perpendicular slope is going to be negative 1. And the equation of the normal line is y plus 2 equals negative 1 times x minus 1. And just a little bit of review for which values of x is m of x not differentiable. A function is not differentiable if it's not continuous, if it has a vertical tangent, and if it has a corner or a cusp. This rational function, the only candidate for one of those is for it to not be continuous. And it's not continuous when it has either a whole or a vertical asymptote. So we should just factor it and make sure if we can. And well, it turns out we can't factor the top because it's just not factorable. So this expression is fully factored, and we can see that there are no factors that cancel out. So it doesn't have any holes, but it does have a vertical asymptote when the bottom is equal to 0. So if I set the denominator equal to 0, I get, add 1 to both sides, 2x equals 1, x equals 1/2. So it has a vertical asymptote when x equals 1/2, meaning it's not continuous. So this graph is not continuous at x equals 1/2, and therefore not differentiable at x equals 1/2.